Hello, everybody. Welcome to Bed Talks again, and I hope you're doing well. So today what we're going to tackle are double integrals with polar coordinates. Understanding why and the motivation behind polar coordinates, understanding how to transform a double integral into polar coordinates, and then trying to do some problems with it and trying to see why this helps us out, why this may not help us out, and so on. So that's the first thing I want to try to do is at least explain maybe the motivation behind this. So for instance, if I have some integral like this, f of x, y, dA, right? We have a lot of different options for this domain D, right? We saw general regions last time where we could describe a region in terms of x and y, but this domain D, you can describe it as in many different ways. And sometimes it might be beneficial for you to use different coordinates to describe it. So for instance, let's assume this D is actually a disk x squared plus y squared is less than or equal to 1. Let's assume that this is the case here. So this is a circle of radius 1, kind of like that. Now, if I wanted to describe this circle just in terms of x and y, right, what would I have to do? Well, again, as we talked about prior to this, right, what we have to do is we would draw horizontal lines to find our bounds for y or x or something like that, and then find our bounds for the other one too. So let's try to do that for this one. So let's assume that I'm taking this with respect to y first. So I'm going to draw vertical lines, right? Drawing horizontal vertical lines like this. And my goal is to figure out where I'm entering and exiting from, right? Where am I entering and exiting from? So I'm always entering the region from the bottom part of the circle, and I'm always exiting the region from the top part of the circle. Now, it's a little bit tough to describe this, but what we can do is I know this circle is x squared plus y squared is equal to 1. And if I want to find my bounds for y, right, I'm going to need, here at least, I'm going to definitely need to try to get two functions of x that bound it. In this case, what I can do is I can actually solve for y here. And what I can do is I can solve for y. I would get y squared equals 1 minus x squared. And then take the square root of both sides. I will get plus or minus the square root of 1 minus x squared. And what's nice here, at least in this case, right, I can describe this pretty nicely because I know the positive branch is the top part of the circle, and the bottom part is negative 1 minus x squared, so something like that. And so I can see that I'm always entering the region from y as negative 1 minus x squared, and I'm always exiting the region from 1 minus x squared here. Something like that. Okay? Now, where would my x be going from if I was to describe this? Well, it's just the most leftmost point and the rightmost point. So I'm always going from negative 1 to 1 here. And so that's how I can describe my region. Now, I want to just reference something. So the area of any region, if I want to find the area of a region D, it is just equal to the double integral of 1 dA. Right, 1 is in that, because again, f of x, y here could be thought of as the height, right? And what's interesting here is kind of thinking about this. I know it sounds silly, but why does this make sense, right? Imagine if I had this great Lysol can here, and I wanted to find, the area of maybe, the volume of this, right? Well, the volume of this, would you agree, is just the length as the area of the base times the height, right? Let's assume the height is 1. Well, that would just be the area of the base times 1. So it would just be the area of the base. So that's why the function height, for instance, in f of x, y, if it's 1, it actually tells me the area of the base. So what if I wanted to then, calculate the area of this base? Well, if I use this exact, if I want to calculate the area of this domain, if I use this exact, formula here, I would get 1 minus x squared, square root of 1 minus x squared, negative 1 to 1 dA. Well, I would have to do, sorry, d, I can even make this a little bit more specific. I integrate with respect to y and then with respect to x. If you can probably see this, right, if I integrate this out, just first off, right, I'm going to integrate this, and my first iteration of the integral is going to be 2 times the square root of 1 minus x squared dx here. This is very ugly to do. I'm going to use trig sub to solve this. Right? And if I want to know that, I know the area of the circle, right? I know the area of that circle. That circle is just pi r squared, so it's just pi here. And I'm gonna have to get pi out of this, so I'll have to use trig sub to solve this. So as our old friend Billy Mays once said, There's gotta be a better way, right? There's gotta be a better way. So how do we do this? Well, maybe there's a better way to describe it. Well, just think about it this way. If I then think about polar coordinates, this is where polar coordinates kind of comes into play. So now what I'm going to do is I'm going to assume, again, the idea of polar coordinates is as follows, right? If I have any point x, y, I then can tell you maybe some other point. I can tell you how far away I am, and I can then tell you what the angle I'm at from the origin, from the x-axis is, that angle there. And we know that we can describe this point as r theta, and I know my combination is x equals r cosine of theta, and y is equal to r sine of theta. Here. Okay, so if I just have a circle, right? If I just have a circle, how do I come up maybe describing this in terms of r and theta? How would I go about doing that, right? Let's say I wanted to find this. So r here, what you want to do, if you're trying to find the bounds for r for something, you always start from the origin, okay? You always start from the origin because r is the radius. It is how far away you are from the origin, right? That is the idea of r here, specifically. If you have a circle going over, like maybe you're thinking about a circle in, you know, like all the way, maybe in a different point other than the origin, you do not start r at the center of that circle. You always start r at the origin, specifically. R here is the radius away from the origin, okay? Now, with this in mind, what we do here is we just start drawing arrows everywhere, straight arrows, okay? Something like this. And what my goal is to see where are my radii. Now, radius can't be less than 0. And I see that the radius, my origin here, is in my domain. And regardless of wherever I go, my radius is always in my, the 0, the origin is always in my domain. So the radius would be at the bottom part of 0, okay? It would be at 0 to start off with. It can't be lower than 0. And the radius of 0 is there. Then where do I always exit the region, right? Where do I always exit the region? I'm always exiting the region at the edge of the circle. If I'm going at the end of the circle here, well, what this circle here is x squared plus y squared equals 1, right? And we can see here the radius is 1. Well, maybe more precisely, just as a reminder, right? We have x squared plus y squared is equal to 1. I can replace, x squared plus y squared is equal to r squared, right? That is my formula to kind of go from x squared and y squared. So I can just replace this with r squared. And then I can take square root, and I'll get r to be 1, noting that we can't have r to be -1 because that doesn't make sense. So this says that my radius goes from 0, and it starts at 0, because that's in my region, and exits the region at 1, okay? Now, theta here is how I have to kind of sweep. So now I start at the x-axis, and now I sweep all the way around, right? I sweep all the way around and try to get as much of the circle as I can, right? Starting at 0, and you're always going counterclockwise. You must always go counterclockwise here. That's a really important fact. If you're not going counterclockwise, you're gonna get something wrong there. So here I see that I'm starting at 0 here, 0 here, this is pi over 2, right? This is pi, theta's always in radians. And we go around in this direction. I know I have a full circle, and a full circle is 2 pi. And so that could be describing my circle here. So think about the difference here. I can describe the circle in terms of this, where x and y here, in this pretty complicated manner. But if we look over here, this is really, really nice. It tells me that the radius, all the points that are from, 0 away from the origin to 1 away from the origin, as well as all of the points going from 0 to 2 pi, go a full circle. So I have that. And what you can note here is all of these are constants, which is great. All of these are constants. And that's so important because if I have all constants, as a reminder, in x and y land, if I had that, that was a rectangle. If I have all constants here, this is also a rectangle, but in polar length. So this is actually called a polar rectangle. And a polar rectangle is when I have all constants for r and theta, and I can describe a region like that. And that, as you remember, we have a lot of really cool things if I have rectangles, right? If it's a separable function, I can separate them into 2 integrals and individually, take that, and so on. So now, with this in mind, how do we then continue with this, right? How do we now, evaluate maybe the area, right? Because as a reminder here, this is kind of where this starts to become a little bit interesting, right? Because I have this right here, right? I want to evaluate this, right? This is the area of D. And I know this differential here, this dA, we usually had this as dA is equal to dx dy. Now think about why that works, right? My area differential here, this is a differential, right? The area differential here should be of a form of length squared. I hope you'd agree, kind of dimension-wise, right? Area is length times width. And we see here that x is a length and y is a length. So length times length equals length squared, which is pretty nice. And now you might say to yourself, okay, well then, I have r and theta. Can I not just make this dr and d theta? And you might say to yourself, okay, that could be valid, but let's think about why this might not be the best case. Does this actually physically make sense dimension-wise? dA here is a length squared. I need a length squared. The radius, I would agree, is a length scale, right? A radius is a length scale. Is theta a length scale, though? It's not. It's nothing. Radians are really almost unitless. It's radians, so it doesn't really mean a lot. So we need something else multiplied by dr d theta to make our dimensions make sense. And because of that, the only other length scale we have here is r. So we just multiply this by r. And this is what we change to, always. Okay, so what's nice here is, if I want to convert to polar coordinates, I'm allowed to just convert to polar coordinates as dr d theta, but I must multiply by this r. This is a huge thing to remember. You must multiply by this r always when I convert to polar. As well, wherever I see f, if I have something like f of xy in there, this must change to f of r cosine theta and r sine of theta. So every single place that I see in my integrand, x and y, I need to replace with r cosine theta and r sine of theta. If I see an x squared plus y squared, I can just replace it with r. So let's kind of do this here. Let's kind of find the area here. So again, what I'm going to do is the area of D here. Now I have my radius and my theta here, bounds, and I can integrate really in any way, right? Because it's r and theta. So I'm going to go from 0 to 1. Usually it's customary to have the radius first integrate, and then I go from 0 to 2 pi. I now have to, because this integrand is 1, I really don't have to change anything. And now I have to multiply it by r dr d theta. This guy. Right? I need to have that r. And from this point, I can integrate. And I can integrate this actually pretty nicely. Even more slickly, right? I note here that this is actually a separable function. Because I have a function of r times a function of theta. So I can split this up. And because I have that this is all rectangle, these are all constants, so I'm allowed to do this. So by using that separability condition, I can separate this out into 0 to 2 pi times d theta and 0 to 1 r dr. Something like that. The integral from 0 to 2 pi of just 1 d theta is just b minus a, so it's just 2 pi. The integral of r squared, r is just r squared over 2, evaluated between 0 and 1. So it just becomes 2 pi times 1/2, which is pi, which is an area of a circle, which makes sense. So kind of like putting everything together really quickly before we start getting into more complicated problems, right? Before we start getting into more complicated problems, what does this tell us here? This tells us the following. If I do have a way to describe a region, maybe where my radius is between 0, A and B, here, R has to be always greater than 0, so it has to be between that. Maybe then I could also describe theta between two values too, so some polar angle. So what am I actually saying here? I'm saying something like this. This is kind of a polar rectangle here. If I can draw this out. So this right here, this is an alpha. This right here is a beta, right? That's my angle here, in that case. And then from this point, right, this right here is a radius of A, this right here is a radius of B. And I could describe it that way. And this region can be described in that exact way here. If I can describe it in that way, what I can do then is say the following. The integral of f of xy dA over my region D, let's assume this is a region D here, okay, is equal to, what I do is, again, I can just have another region D, but now this is converted to a polar rectangle, right? I convert everything to polar. I replace all of my x's with r cosine theta, all of my y's with r sine of theta, and then I multiply this by r dr d theta, making sure we multiply this by r dr d theta. And this right here is a polar coordinate transformation, okay? Now, this might not work always. I mean, it might not be beneficial for you to do this. So a couple of main things you should check out. First off, if I'm able to describe this much better in polar rather than Cartesian, you might want to. If you see something in the integrand that might be simplified, right, that might be a really important thing too. If you see like an x squared plus y squared, I mean, that converts to r squared. It's really nice. So, you know, if I can convert things like that, it's pretty helpful. So let's do an example to kind of show you how I would go maybe about this. What I'm going to do here is, this is a problem that's in the textbook, but I'll at least do it here to kind of show you a problem that we do. So let's assume I want to calculate the double integral of over this region D of x squared y dA, where D here is x squared plus y squared is less than or equal to 25. It's a radius of 5, a circle, okay? And it's just the top half of this circle here. Now think about what this means again, right? Physically, what does this mean? This is the net volume of this function height, x squared y, whatever that is, over the region D, which in this case is the top half of a circle of radius 5. And it's the net volume from there to the xy plane. This could be negative, it could be positive, right? It could be anything. So let's draw this region D. It's always very important to draw this out. It's a really important thing, so you can visually see and you can draw these lines as we just kind of did before. So this is my region here, my region D. That's from -5 to 5. I have 5 here, and it's just the top half, right? Now, you could theoretically describe this in Cartesian. You definitely could. How will you describe this in Cartesian? Well, you do have here, right, you do have these horizontal, or you can do these vertical lines pretty well. You can say that y is from 0 to the top half of the circle, right? You could do that, and you can say x is from -5 to 5. So maybe you could do something like, 0 is less than y, and then, the square root of 25 minus x squared. X is from -5 to 5. But if I take a look here and then plug this into there, I don't know if I really want to go ahead and do that. I'm going to have the square root. It's going to look pretty nasty, honestly. It might not be too bad to do it, but there's probably a better way to go about it, especially since I have a circle here, right? This is a circle, and this is described very, very nicely in constants with a polar coordinate transformation. So how do I do this again? I start from 0 here, and I go out, right? Kind of go like that. Here. All right, I go out. I start at the origin, and I go out. Now, 0 is in my region, right? Every single time I'm entering the region from 0, always, because 0 is in my region. So I can describe this on the bottom of 0, and I'm always exiting from the radius of 5, which is that circle, right? Always exiting from there. Kind of going like that. Now, how about theta here? Where's theta running from? Well, theta, I have to be sweeping in this direction, right? I have to sweep in 0 to that direction. I have to kind of go in that direction here. So if I'm doing that, right, I see that I'm starting at 0 and I'm sweeping all the way to the other side, which is pi here. I don't go any farther, right? So I'm going from 0 to pi. 0 to pi. And this is the way to do it. That's not too bad. Right? And again, I describe this as a polar rectangle now. And now what happens is if I want to convert this to polar coordinates, customarily we usually let r be first because sometimes r is dependent on theta. Theta will really never be dependent on r. So usually integrate theta last. That's just usually how we write it. It's really up to you though, especially if it's a rectangle, right? If r is dependent on theta, you must integrate that first, right? We might do a problem or two, and maybe in a different video or something like that to kind of go through it. But here, I'll go from 0 to pi. Then what I do is everywhere where I see x and y, I replace it with r cosine theta and r sine theta. And then the important thing that you always need to remember is that I need to multiply this by r dr d theta. You must multiply it with that r, right? Because we need to keep the dimensionality the same. Okay. Now, if I simplify this out, I would get r squared times r, right? The r squared from the first term and then r and r. So I'm going to get, in that case, I'm going to get r to the fourth. I'm going to get a cosine squared of theta, and I'm going to get a sine of theta, dr d theta. And you might say to yourself, well, I mean, this doesn't seem a lot better, but it definitely is. And the reason why, again, is this is a separable equation. A lot of times these problems are going to come with separable equations, which is really nice. So you can integrate, especially if this is all constants, right? It has to be all constants. You can then separate them and integrate them individually. So here, if you notice, right, r to the fourth multiplied by another thing in theta. So I can separate these. And I can integrate this from 0 to pi of cosine squared of theta times sine of theta d theta, and then 0 to 5 of r to the fourth dr. This is pretty nice to integrate. This right here, I mean, this is just, honestly, it's going to become just 5 to the 5th over 5. So it's just 5 to the 4th. Over here, though, to solve this integral, now it's just a one-dimensional integral, we would probably want to use u substitution, right? U for cosine. Here, if I let u be cosine, I would get a negative sign, right? So I'd have to kind of work with that. But because of that squared, I'll probably want to do a u sub. And so this is kind of what you would do. And now it's, I mean, I can just solve this out if I wanted to. I'm going to stop there for the time being. But this is at least a really, really beneficial way of going about these problems, right? I can convert it to polar coordinates, and I can really take advantage, especially if it's a polar one, I can really, really take advantage of, you know, trying to figure out and trying to integrate something like this, right? And trying to figure out, you know, making this a rectangle and going from there. Okay. And the last problem I'm going to do is actually going to be a little bit more complicated, just to show you at least where this could go, and why even polar coordinates are so much more beneficial, especially to solve some of these problems too. So the problem I'm going to solve here is I want to find, this is again a problem that we see in the textbook. So I want to find the volume below the cone z equals x squared plus y squared. I'm sorry, above the cone. That would make no sense in this problem when also. So above the cone, z equals x squared plus y squared, square root. And then below the sphere of z, x squared plus y squared plus z squared is equal to 1. So I'm going to find the volume of this. Okay? Don't know what that is. So the first thing you want to do is just going to draw this as best as possible. So let's kind of draw this here. If I can draw a straight line. Like that. Okay. So the cone here, this is just the top half of a cone because we have a plus or minus. There's no plus or minus out in front, so it's just the plus. It's just that. So let's kind of draw this cone. Just going up in this direction here. You would get something like that. And it's below the sphere here. So what I want to do, I'm going to make this a little bit bigger here. So just give myself a little bit of room. And then I have this sphere here. It's a radius. This sphere is centered at the origin, has a radius of 1, and just kind of comes down. Right? Kind of comes down like that. And you kind of see what happens here. Right? It kind of creates like this ice cream cone. Because it's below, right? If I kind of, because it's below this cap, right? It's getting capped, and then it intersects the cone at some point. So it's like an ice cream cone, right? You have the cone, and you have the ice cream top. And my goal is to find the volume of that. Okay? My goal is to find the volume of that thing. Now, This is where it starts to get a little bit hairy, right? What is the formula for volume, or how do we do volume, at least in double integrals, right? There's ways to do it in triple integrals. It's the same process, which is really nice, with just an integrand of 1. Let's think about this in double integral land. As a reminder, this thing right here, f of xy dA, this gives us, a way for us to describe this. Right? It gives us a way to describe the volume of an object. Where f here, this is considered the height. Okay, this is the height. So what do I mean by height here? This means I need to figure out, if I pick an xy point, right, how tall is this going to be, right? Where am I entering the region from, and where am I exiting the region from? So think about it this way. I'm going to draw it like this. I'm going to draw these guys. And I'm going up in this direction, right? Well, if I'm going up in this direction, where am I always entering from? I'm always entering from, I hope you'd agree, the cone. I'm always entering from the cone. Enter from the cone. And I'm always exiting from the sphere. So my height really is the height of the sphere minus the height of the cone. Something like that. Well, I have to be a little bit careful, because I would need to convert this to something I'll be able to use a little bit more. So what I could do here is I could solve this for z and get the square root of 1 minus x squared minus y squared. Again here, what I'm doing is I'm not taking the plus or minus route, because I'm just talking about the top part of the cone. So my height here, my f of xy, can actually be this height, which is the top height, subtracted from this height. So something like 1 minus x squared minus y squared minus x squared plus y squared. Something like this. And this right here is my height. Let's kind of zoom out just so we can kind of see this whole thing in action. Okay, so make sure you're okay with this step before we go forward anymore. So again, I now know what this function is going to be. Now, how do I figure out, and this is probably the tougher part here, how do I figure out my domain, right? My domain in x and y. Because what I've done here is I've kind of integrated out z already. I told you the height. And now what I do, since I've done the height, I project this surface. This is what we do. We project this entire thing onto the xy plane. If I project this onto the xy plane, would you agree, like this circle right here, if you look from the top, this circle that I'm circling here, right, that circle would be the thing that would be projected. Right? That would be the domain that I'm kind of worried about, right? That's the fattest part of that ice cream cone. Imagine I'm looking at the ice cream cone, right? I'm seeing the biggest part of that end right there. And so if I kind of draw this out in the xy plane here, kind of just like that, it's just this circle. And that's what's being projected downwards, right? That's the entire circle. So now, I know I can describe a circle really well with polar coordinates. So let's do it. However, there's one last thing I really need to figure out. What's the radius of that circle? It's not too obvious what that radius of that circle is. It's not. It genuinely is not. So how can we figure that out? Well, would you agree that it's really the intersection of the cone and the sphere, this circle here? It's the intersection of that. So how do I find the intersection of two things? Well, I have the cone here. I have the sphere here. They're at the same z, right? So what I could do is actually equate both the square root of x squared plus y squared and the square root of 1 minus x squared minus y squared. If I equate those, that gives me the intersection, because I'm telling you where I'm at the same z point at. So to find my intersection, and this is why this problem gets really just kind of crazy here. To find my intersection, what I need to do is solve for the square root of x squared plus y squared is equal to the square root of 1 minus x squared minus y squared. Where does this happen? That's my goal. So now, in order to solve this, I square both sides. I do that. I can move over the x squareds or y squareds and move them all together. So this becomes 2x squared plus 2y squared is equal to 1. And then what I can do from there is I can divide out by the 2 and get x squared plus y squared is equal to 1/2. And so what does this tell me? This tells me that the radius of this circle, is the square root of 1/2. Maybe a little bit written a little bit better, right? This is 1 over the square root of 2, or maybe more affectionately known as the square root of 2 over 2. And that's my radius. So think about what we did there. We projected the surface down. The surface that we saw going down is a circle. The radius of that circle is the intersection between the sphere and the cone. To find the intersection, what we do to at least find what that is, right, we equate the cone and the sphere. And we just solve it out, and we get a circle. And that circle has a radius of the square root of 1/2, or radical 2 over 2. So this means, and this is why this comes into play really handy, right? I now know that the radius of the circle is the radical 2 over 2. And so if I want to find my domain here, my domain D, can be described very, very quickly with r and theta, because it is a circle. I have a full circle, right? I have a full circle, so my theta is going to be between 0 and 2 pi. I know that off the bat. If I have a full filled in circle here, like this, right? I'm starting my origin here is at 0, so I'm always starting there. My radius here goes out to the radical 2 over 2. And that's my domain. And so therefore, with this whole thing in mind now, we can now actually write down what the actual volume of this thing will be. Okay? The volume here of, I'll just call it volume, is going to be equal to, we know it's the double integral of d f of xy dA. But now what I'm going to do, I know f of xy here, I know f of xy is actually in this form, right? So what I'm going to do now is I'm going to replace every instance of x with r cosine theta, every instance of y with r sine theta. As you can see here, this really is this thing right here is really 1 minus x squared plus y squared. So the inside here, this becomes actually 1 minus r squared. Out here, this one is really just going to become r, because x squared plus y squared is r squared, and the square root of that is just r. So if I go ahead and do that now, my integral is going to be between 0 and square root of 2 over 2, and 0 and 2 pi. I'm going to have my function be the square root of 1 minus r squared, that's coming from this portion right here, minus r, which is coming from this guy. Right? Then I have to do dr d theta. And more importantly here, I always have to add this r in. And this integral right here gives me the volume of this ice cream cone here. That's kind of it. We can solve this integral out relatively well, because we also know that there's no theta dependence, so we can separate them. I'm not going to go through this. I'm going to go through this a little bit quicker, because you can feel free to skip this if you don't want to see how to skip it, if you want to see how to do it. There's no theta dependence, so I can just do that part. I can then do 0 to the square root of 2 over 2 of r times 1 minus r squared minus r squared dr. This portion right here will just be 2 pi eventually, which is nice. This one right here, if I'm going to solve this out, I probably should use u substitution. This individually can be done individually, right? In this, I can kind of, separate these two integrals if I wanted to, at least this part, right? Square root of 2 over 2 and r 1 minus r squared dr. And then I can do minus 0 to square root of 2 over 2 r squared dr, right? This can now be solved pretty quickly. This one, if you're going to solve this, you probably should utilize u substitution. Leave 2r, something like that here. And then go for that. But this will now give us our volume if I go through this whole process. So what did we show here? Right? What did we do? We took a pretty complicated problem. I'm trying to find the volume of this thing. It looks actually very complicated. But in actuality, what is it actually saying? Well, I can rewrite my volume as something like this, where f of xy is my height. My height here, I know the top part was the sphere, the bottom part was the cone. We subtracted them off. Then we projected the surface down, because I've integrated out z almost. I've kind of integrated out my height, so I project it onto the xy plane. I project it onto the xy plane, I get a circle. The circle is actually the intersection of the sphere and the cone. What is that radius? Right? It's not obvious. It's not 1. Be very careful that it's not 1. So what does we do? Well, it's really the intersection between the sphere and the cone. We put this over here. We solve it out. We see that this actually becomes x squared plus y squared plus 1/2, which means that the cone has a radius of square root of 2 over 2. We can then go back here and write this radius down, 0 to the square root of 2 over 2, theta from 0 to 2 pi, because it's a very quick circle. It's nice like that. And then we just set this up like this, making sure we don't forget this r d theta. And then we just go ahead and solve through this whole thing. Make sure you can use u substitution pretty well and go from there. So that's basically it. Honestly, polar coordinates are really, really handy. And as we can see, just even back here, asking the very basic question of what the area of a circle is really hard to talk about in Cartesian, but almost trivial in some way in terms of polar. That's kind of why we need that r. If we didn't have that r, right, we wouldn't even get pi. So we need the r d theta to kind of make their differentials make sense, right? We're gonna have to think about this when we go to 3 dimensions. We have a couple different types of, coordinate transforms. So we'll have to think about that going forward. But that's basically it here. I hope this makes sense. If you want to keep rewatching it a couple times, feel free to do that. Let me know if you have any questions, either in the comments or on Piazza or something like that. And yeah, I hope this makes sense here. I hope you're doing well. And yeah, I'll talk to you soon. Thank you for coming to Bed Talks, virtual.